All right. Hi there. I'm back. I'm having so much fun with the balloon demonstration that I thought we should do one more. So I've got this nice yellow balloon. All right, that's it. Did I have you in suspense there? All right, I really want to try to tie this one. Oh, I think I've almost got it. All right, there we go. Okay, so I blew up this balloon and it didn't pop. So this represents a series that converges. So now suppose I take this balloon and I blow more air into it. Will that balloon pop or no? Well, the correct answer is we don't know, right? It depends on how much more air I blow into it. So the moral of the story is if you have two series and the smaller one converges, that is not going to help you figure out what the bigger one does. And the same thing goes for if I took this balloon and I blew it up until it popped, right? And then I took this balloon and blew less air into it. Well, again, I don't know, right? So if your bigger series diverges, that doesn't tell you what the smaller series does. So you have to be very careful with the direct comparison test. And if you find that your inequality is going in the wrong direction, what you might be able to use is, whoops, sorry, I'm in the wrong place here. Darn it. Oh my gosh, the limit comparison test. Okay, so what you see in front of you is the limit comparison test. I mostly only use number one of this. However, you are free to use numbers 2 and 3. I'll explain them briefly. Suppose that a sub n and b sub n are both greater than 0 for all n greater than or equal to some integer n. So eventually you have two series that eventually both have all positive terms. If the limit as n increases without bound of a sub n over b sub n is equal to c, where c is a finite positive number, then the series a sub n and b sub n either both converge or they both diverge. So the idea here is that if the ratio is tending towards a finite positive number, then that means that those series are growing proportionally to each other. And so if one of them converges, the other one should converge. And if one of them diverges, the other one should diverge. Very briefly, number 2 and 3. If the limit as n increases without bound of a sub n over b sub n is equal to 0, and the series b sub n converges, then the series a sub n also converges. So the idea there is that the series a sub n is growing much smaller than the series b sub n, growing much more slowly, I should say, than the series b sub n. And so if b sub n converges, then it stands to reason that a sub n will also converge. And the flip side of that, number 3, if the limit as n increases without bound of a sub n over b sub n is equal to infinity, and the series b sub n diverges, then the series a sub n also has to diverge. So the idea there is that the series a sub n is growing much, much more quickly than b sub n, and we know that the series b sub n diverges. But again, I will mostly use number 1. Oh, I just realized there we go. All right, I had a little bit of a panic moment there because I had accidentally deleted, I think, like 4 of my slides. So thank goodness for Command Z, or if you're using Windows, Control Z will undo whatever it was that you just did that you didn't want to do. All right, so here are the examples. Let's go over to the tablet. All right, starting with the sum n going from 1 to infinity of the square root of n plus 1 over n squared plus 2. So let's talk first about why would it be difficult, if not impossible, to use the direct comparison test on this. Well, if I was trying to use, excuse me, direct comparison test, I would again go with dominant terms. Okay, so I would look at the square root of n over n squared. So the problem here is that the numerator is bigger on the left-hand side, but the denominator is also bigger. So those two things are kind of working against each other. So I don't have a really clear idea of how these two things compare to each other. However, whenever you find yourself in that situation, it means that you can probably use the limit comparison test and for your second series, use the series that you were trying to compare it with. So that would be the square root of n over n squared, which is the square root of 1 over n, which is 1 over the square root of n. All right, so this will be my a sub n. This will be my b sub n. So let's look at the limit as n increases without bound of a sub n over b sub n. Limit as n increases without bound of square root of n plus 1 over n squared plus 2 over 1 over the square root of n. And then instead of dividing by 1 over the square root of n, I will multiply by the square root of n over 1. So that'll give me limit of the square root of n plus 1 over n squared plus 2 times square root of n over 1. So now if I multiply those together, because those numerators are both under square roots, that means I can multiply the radicands together. N times n plus 1 is n squared plus n, isn't it? All right, so now technically what I'm going to do next is push that limit inside the square root. I wouldn't be too upset if you skip this step. That is a property of limits because square root is a continuous function. All right, so now hopefully you learned in Calc 1 about limits and infinity of rational functions. All you have to do is look at the dominant terms. And if the dominant terms have the same degree, then the limit is just the ratio of the leading coefficients. So in this case, this limit would be 1 over 1, which is the square root of 1, which is 1. 1 is a finite positive number. All right, so we're almost done with this one. So let me just make a little bit of room up here. And then what do we know about the series n going from 1 to infinity of 1 over the square root of n? Well, I think we've encountered that series before in this very lecture, right? We know that series diverges because it is a p series with p equal to 1/2, which is less than or equal to 1. That means that the given series, n going from 1 to infinity of the square root of n plus 1 over n squared plus 2, also diverges by the limit comparison test. All right, next example, the sum n going from 3 to infinity of 5n cubed minus 3n over n squared times n minus 2 times n squared plus 5. Actually looks like a fun partial fractions problem. Okay, well, I'm not going to bother trying direct comparison test this time because I see well, just in the denominator, I have a mix of pluses and minuses. So I don't think that I'm going to be able to get a very clear read on how this denominator compares to n squared times n squared. Okay, so let's just go right to the limit comparison test. And let's use the limit comparison test with the sum n going from 3 to infinity of 5n cubed over n squared times n squared, which is n to the 5th. And that's equal to 5 times the sum n going from 3 to infinity of n cubed over n to the 5th, which is 1 over n squared. So already we have an idea of, a good guess for what this series is going to do because we know what the sum of 1 over n squared does, right? Okay. So let's set up this limit. So this is going to be a sub n, and I'll leave out the 5. We don't need the 5. Just make this b sub n. And then the limit as n increases without bound of a sub n, 5n cubed minus 3n over n squared times n minus 2 times n squared plus 5 divided by b sub n. And now instead of dividing by 1 over n squared, let's just skip right to the part where we multiply by n squared over 1. That's going to give me this nice rational function whose numerator is 5n to the 5th minus 3n cubed over n squared times n minus 2 times n squared plus 5. All right, so all you need to know about this is that the dominant term upstairs is 5n to the 5th. The dominant term downstairs is n to the 5th, which means that the limit is the ratio of the leading coefficients, which would be 5 over 1, which is 5, which is finite and positive. And as I mentioned a moment ago, since the sum n equals 3 to infinity, 1 over n squared, what does that do? It converges. It is a p-series with p equal to 2, which is greater than 1. And I should also mention this series starts at 3, n equals 3. I believe at the very end of section 10.2, we talked about the fact that leaving out a finite number of terms does not affect whether the series converges or not. So normally we start a p-series at n equals 1, but that doesn't matter. I'm just leaving out the first 2 terms. All right, that means that the given series, the sum n equals 3 to infinity of 5n cubed minus 3n over n squared times n minus 2 times n squared plus 5 also converges by the limit comparison test. All right, that brings us to our last batch of examples. The instructions for this set of examples said use any method to determine if the series converges or diverges. So let me just say a few words about the direct comparison test versus the limit comparison test. I tend to try to use the direct comparison test when I can because it tends to be a little easier. The problem is that it sometimes takes a little bit more insight because remember that inequality has to go the right way. You either have to find a larger series that converges or you have to find a smaller series that diverges. All right. And that's something you get better at with practice. And as we showed in some of the previous examples, if you can't get that inequality to go the right way, then chances are you'll be able to use the limit comparison test. For this one, I will use the direct comparison test. So first note, for the direct comparison test, both of the series you're using, the given one and the one you're comparing it to, both have to have positive terms, at least eventually. All right, so as we've noted many times, cosine of n is between -1 and 1. So that means 1 plus the cosine of n is between 0 and 2. And therefore, 1 plus cosine n over n squared is between 0 over n squared, which is 0, and 2 over n squared, all right? So these are the two series that I'm thinking about using. And they are both series with positive terms. All right, so let's look at 2 over n squared. So this will be my, oh, it doesn't matter. I was trying to remember the notation they used. So we'll just say, look at the sum n going from 1 to infinity, 2 over n squared, which is equal to 2 times the series 1 over n squared. All right. This series here without the 2 is a p series with p equal to 2, which is greater than 1. Therefore, that series converges. And then I will just briefly point out that when you multiply a convergent series by a number, you get another convergent series. That was a theorem in section 10.2. Multiple of convergent series also converges. All right, so we have found a bigger series that converges. So now we can say, therefore, by direct comparison test, the sum n going from 1 to infinity of 1 plus cosine n over n squared also converges. All right, next example. All right, the sum n going from 1 to infinity, n minus 1 factorial over n plus 2 factorial. So you're going to want to pay attention to this trick that I'm going to use because we're going to be using this a lot. I think maybe starting in the next section or the section after, when we get to a test called the ratio test, we're going to be doing a lot of stuff with factorials, and this trick will come up a lot. So let's just pull out that general term. I'm going to say note n minus 1 factorial over n plus 2 factorial. All right, we know n minus 1 factorial means n minus 1 times n minus 2 times every smaller number until you get to 1. And n plus 2 factorial means n plus 2 times n plus 1 times n minus 1 times every smaller number until you get to 1. So what I am trying to tell you is that this expression and this expression are exactly the same. So we can cancel those out. So it turns out that n minus 1 factorial over n plus 2 factorial is equal to 1 over n plus 1, n plus 2. Okay, so I think it might be a little simpler to deal with the series in that form. And this is another case where the direct comparison test will work, because I would really like to compare this to 1 over n cubed. That series is another convergent P series. And fortunately, n times n plus 1 times n plus 2 is less than that because it has a bigger denominator. All right, so the sum n going from 1 to infinity of 1 over n cubed converges because it is a P series with P equal to 3, which is greater than 1. Therefore, the sum n going from 1 to infinity of, I'm just going to write it the new way, 1 over n plus 1, n plus 2, also converges by the direct comparison test. All right, and that brings us to our last example. The sum n going from 1 to infinity of the tangent of 1 over n. So this is one of those cases where it's really not all that obvious what to do at first. You get better at this with practice. So my dominant term trick that I was talking about doesn't work. So I'm just going to cut right to the chase and tell you what does work. I am going to use the limit comparison test with the series n going from 1 to infinity of 1 over n. Okay. All right. So this will be my a sub n. This will be my b sub n. So we need to look at the limit as n goes to infinity of a sub n over b sub n, which is the limit as n approaches infinity of tangent 1 over n over 1 over n. And I think we've encountered this limit before. What I like to do with this limit, and by the way, this is technically a Calc 1 limit, I am going to substitute, you've seen me do this before, I'm going to substitute u for 1 over n so that I can rewrite this limit as the limit of tangent u over u. And now as n approaches infinity, 1 over n approaches 0 from the right. And now, again, it's a Calc 1 limit. I could write it in terms of sine u over u, which is definitely Calc 1, but I'll just use L'Hopital's rule. So by L'Hopital's rule, because this has the form 0 over 0, this is equal to the limit as u approaches 0 from the right of secant squared u over 1. That limit is secant squared 0, which is 1 squared, which is 1. Woohoo! And the reason I'm happy about that is because whenever I use the limit comparison test, at least the first version of it, the one that I said is practically the only one I use. I'll use one of the other two if I get desperate. I want that limit to come out to be a finite positive number. So I'm going to finish this off by saying since the sum n going from 1 to infinity of 1 over n diverges. And in terms of the reason why it diverges, you could either say that it is a p series with p equal to 1, which is less than or equal to 1. Or you can say it's the harmonic series. The harmonic series is this one particular specific series. So we'll just take it as a known fact that the harmonic series diverges. We actually proved that back in, I think it was section 10.3. The sum n going from 1 to infinity tangent 1 over n diverges by limit comparison test. And that's going to do it for section 10.4. We'll see you next time.